Hello everyone, my name is Pedram and I'm a professor in data analytics. Welcome to another episode of Deep Learning. Alright, this is the last theory lecture of Module 5, Deep Computer Vision. Let's wrap up this long but very exciting module with covering some advanced topics in computer vision. Okay, here's a quick recap of what we covered in the past three theory lectures. In part one, we started with comparing human vision versus computer vision, and we covered some of the basic definitions when it comes to deep computer vision. In part two, we specifically dived into CNN architecture, and we talked about different layers, input, conv layer, max pooling, and fully connected layers, and things like that. In part three, we said, okay, how do we know that an architecture is a good architecture? Are there any best practices out there? So we answered these questions. We also talked about interpretable CNN. We saw that how we can visualize, different layers within the network. So for example, how we can visualize the convlet layers, how we can visualize the filters themselves, and finally how we can visualize, something called CAM, class activation map. Then we concluded that part with the concept of transfer learning. Now in this part 4, let's go beyond classification, and we want to talk about more advanced topics in deep computer vision. So specifically, I want to talk about object detection, semantic segmentation, and image captioning. Without further ado, let's get into that. Okay, it might be the case that image classification used to be or is still the bigger chunk of deep computer vision, but there are so many other cool applications when it comes to deep computer vision that I think that you should be aware of, and they're becoming more and more prevalent just because of the more computation powers that you're getting every single day. Okay, so what are these things? Let's start with object detection. Let me use my pen. So this is the object detection one, the first one. What is the task? The task in object detection is to identify and locate objects in an image, right? So the idea is that the output of the model, the output of this task is something like this. We're going to come up with some bounding boxes and labels for the object. So here it means that, remember, in image classification, the output was just some simple label. So we had single output, right? But now we have multiple outputs. We have the labels, and on top of that, we have something called bounding boxes. Let's look at this example. It should make a lot more sense. So for example, we have an image. This is this is a crossroad in New York City, and you want to figure out what are the objects in this picture, right? So you want to figure out the pedestrians versus cars versus dog, traffic lights and things like that. So already we are dealing with multi-label problem, and on the other hand, we also want to figure out where are the bounding boxes, right? So for example, let me use a color that you can see. For example, these are pedestrians, right? And this is a dog, this is a traffic light, and etc. So this is a lot more challenging problem, because not only you need to label multiple objects in the picture, you have to say where's the location of that object as well. So as you can see, this is a multiple output model that you're dealing with, or task that you're dealing with. Okay, the second one is image segmentation. So in image segmentation, we are trying to classify each pixel of an image into a specific category. So computationally, this one is a lot more involved compared to image classification, because remember, in image classification, you're going to process the entire image. Of course, we're going to break it down into, for example, we're going to slide the filter over different batches of data, but at the end of the day, we're looking at the entire picture, right? But here in image segmentation, we're going to label every single pixel. So the output is going to be a label for each pixel in the image. So what is the application? So there's something called the segmentation map. And so for example, this is a segmentation map. And the idea is that when we have already labeled all the pixels, let's say we have a bunch of pixels here, right? And I know that each pixel belongs to what category. So for example, this pixel belongs to sky, this pixel belongs to car, this pixel belongs to street, things like that. Or this belongs to pedestrian. Now we can use all those labeled pixels and put it together and create something called a segmentation map, right? And basically we are segmenting the image into different things like road, car, sky, and you name it. So as you can guess, there's in reinforcement, in self-driving and there's going to be a huge application of this image segmentation. Okay, so that was the second one, and the last one is image captioning. Okay, so as the name suggests, the task is to generate a textual description of an image. So the output is going to be a written description of the input image, right? So for example, this is the input image, and the output is going to be the cat is in the grass. So most probably you have figured it out by now that you are seeing all of these applications around yourself, right? So that's why I think you should know these techniques. And in this course, I'm not going to talk about the details of how we can apply these things with Python. However, at the very high level, I expect you to know what is the theory. Okay, so let's look into the theory of these things one by one. Okay, let's start with object detection. At the core of object detection, there's this concept of object classification and localization, right? As I said earlier, the output of the model is not simply just labels anymore. It's beyond that. Let's look into that new output. So imagine we have an image of a cat here, and let's say if you are just using these axis numbers, so 0, 0 is here, 1, 1 is here, right? So the goal is to, first of all, classify this image, so obviously it's a cat, and localize that cat inside that image, right? So we have multiple objects here to achieve, right? And let's say we're gonna pass this input to our, I don't know, architecture, whatever it is. It can be a combination of conv layers, pooling layers, and then a bunch of activation functions at the end. And then this is the output, right? So the output, as I said before, it's not this anymore. It used to be only this, right? The output used to be what is the probability of cat? What is the probability of dog? What is the probability of bird, right? So if we use it, let's say softmax activation function at the output layer. But now we have these new stuff. So let's see what are those new stuff. So first of all, let me use red maybe. This is the cat, where the cat is, and we're going to find the centroid of that. So this is a centroid, and then we're going to look into the axis numbers for that centroid. So in the x-axis we have, I don't know, for example, 0.6, and in the y-axis we have 0.5, right? So these are the two new numbers, bx and by. So it says that the centroid of x coordinate and centroid of y coordinate, 0.6, 0.5. So we know that where is the centroid of that image that we are classifying. Then we want to come up with a bounding box around it, right? So we have to say, okay, this is BW. BW is basically simply the proportion of bounding box with respect to the overall width of the image, right? So imagine if the total width of the image is 100%, this thing that we are doing, I don't know, maybe roughly is 50% of that. That sounds fair, right? So maybe we are going to say it's 0.5. So if this is 1, so this is where the 0.5 is coming from. And same story for the height, right? So if this is the entire height of the image, again 100% or 1 unit, then our bounding box, this one, is covering this much of it. So probably it's 90% plus, so let's say 0.9, right? So this is where the 0.9 is coming from. So these are the four new numbers, right? Bx, by, bw, bh. And then there is this thing at the very first. We're going to see if the object was detected or not, right? So here, if it is 1, it means that in this picture, in this image, the object that we're looking for, either cat or dog or bird, was detected. So it is 1. Otherwise, it's 0. Okay, now we're going to use these concepts. Basically, now you have a better understanding of what is this new output for object detection. And look into the problem and see what are the challenges, right? So what are the challenges if you have multiple objects? What are the challenges that localizing and identifying these things? Okay, so as I said, object detection is a task that involves identifying and locating the objects in the image. And remember, the model learns to recognize the objects and predict bounding boxes around the new images, right? The objects in the new images. I hope that you're starting to realizing that this is not an easy task, right? So let's look into that why. So imagine this is a picture that we are having, right? And we can go ahead and say, okay, let's go ahead and detect if there's a taxi in this image or not, right? So here's going to be the output. Already the output is we have multiple output, right? We have x, y, width, and height, right? So those basically bx, by, bw, bh, right? But what if you're going to identify multiple objects, right? We want to identify persons, we want to people, we want to identify truck. And as you can see, now we're dealing with multi objects with multi dimensions, right? And hopefully you're, again, as I said, hopefully you're starting appreciating that this is not an easy task, right? Because what are the solutions? Think about the solutions. You can say that let's start with the very naive approach. What should we do? We should say that, okay, let's come up with different bounding boxes, different sizes, and you're going to slide it over the entire image, and then starting, identifying those and localizing those objects, right? So that's a naive approach, but we definitely should do better than that, because the naive approach is computationally very expensive and it's of course very inefficient. So the better solutions are, RCNN, regional based CNN, and it's the augmented version of that, fast and faster RCNN, and obviously the YOLO one, you only look once algorithm. So let's look into those solutions. We're going to start with the naive approach. Okay, maybe the most basic approach that you can think of is the naive approach, right? And what is the idea? The idea is that we're going to scan the image with sliding windows. We will start with placing a random box, literally a random box, both in terms of position and size of the box, somewhere in the image. Imagine we were putting that random box here. Then we're going to pass this random box, that part of the image, into a CNN and make a prediction, right? So imagine we have one of these pre-trained models which have been trained on a multi-class classification of 1,000 different classes of images, right? And then hopefully we can figure out that, okay, the output, the class of this object is, I don't know, cone, traffic cone, right? Then we are going to repeat this with many different random boxes, right? So this is what we're doing. We're going to say that, you know what, let's go try, I don't know, we can think of thousands of these boxes, hundreds of these boxes, and sliding it over and something like that. And as you can see, there's a big problem with this approach, right? And the problems are, first of all, there's too much inefficiency going on here, because again, maybe we are using unnecessarily large number of random boxes in the picture, right? It's going to slow down the process. And we know that this thing is going to be computationally very expensive and too slow for real-time uses. Remember, the object detection application is, most of the time we use it for real-time use cases, right? So imagine I don't know, in a self-driving car, the sensors are basically looking at the surrounding, or basically the cameras are looking at the surrounding, and they want to figure out the objects in front of them, what is it, right? So it should be done in a matter of seconds or milliseconds. Okay, so the naive approach, even though it seems very intuitive and simple, but it doesn't work, right? Because it's very inefficient. The next approach is something called regional-based convolutional neural networks, or RCNN for short. Well, the idea is that we will strategically select interesting regions to run through the classifier, right? And these regions, we're going to call them regions of interest, ROI, and these are the regions that we think they have objects with high probabilities, right? So let's talk about what are the caveats, and then we can look at this image, which is going to help a lot. So the first problem is that, as you can guess, it's very slow. Imagine you want to come up with 2,000 of these ROIs, and you have to pass it through the network. And just like naive approach, this is too much, right? And there is no real-time use cases. Let me actually walk you through this image that I borrowed from Russ. So here's the reference. And so imagine this is your image, this is the input image, and we are visualizing 3 of these ROIs, right, out of 2,000. So out of 2,000, this is 3 of them. Then we are going to wrap that region and then pass it to the network. So we're going to pass it to our convolutional networks. And then at the end of the day, for the output, we can use any kind of regression models to basically figure out what are the bounding box numbers, or we can use any kind of classification machine learning models to come up with different classes. So we can apply machine learning model like SVM, or we can simply use the softmax activation function at the very last layer, right? So this is how our CNN is doing the job. But as you might be wondering, is that what is this ROI? How we can figure out that? What do you mean by these are the regions that have the higher probabilities? So as you can guess, this involves another heuristic itself, right? This involves another optimization, or another search algorithm, which is, by the way, a fixed algorithm. So again, another caveat with this approach is how to define these ROIs, right? The selective search algorithm is a fixed algorithm, so it means that it doesn't get updated during the training. So we come up with a heuristic and for finding those best regions of interest with higher probabilities. But the problem is that they're fixed, they're not learnable and during the training, and more importantly, they are detached from the network, right? So it seems that we are doing all these computation at two levels. First, we have to figure out what are the ROIs by using another search algorithm, right? And this search algorithm is fixed. So maybe this is the first step. And then the second step, now that we know what are ROIs, we're going to pass it to the CNN. Okay, so it seems that these two processes are completely detached. So ideally, if we can combine these two things together and train the network just once, that would be a lot more efficient. And of course, the ROIs are going to be learned during the training. So this is exactly what the augmented version of the RCNNs are going to do for us. Okay, the first improvement to RCNN is something called fast RCNN. So the approach to fast RCNN is similar to RCNN, simply we are dealing with these ROIs, but instead of converting, let's say, 2,000 of those ROIs into the corresponding feature maps, we're going to convert the whole image once. So what does that mean? Remember, previously we used the image, we come up with the ROIs, and we pass the ROIs to the convolutional layers to get the feature maps separately, right? But now we're going to do it only once. We're going to use the entire input image, pass it to a convnet, come up with some high-level feature maps, right? And then for those high-level feature maps, from those feature maps, we are going to apply our, I don't know, our heuristic, our search algorithm to come up with, let's say, 2,000, let me use my pen, let's say another 2,000 region of interest, right, ROIs. So, but the point is that these ROIs are, the search algorithm is using the feature map to figure out those 2,000 ROIs, right? So then we want to pass it to a fully connected layer, but there's a problem here, right? Because we know that for fully connected layers, or even for CNN, we cannot use different input shape size, right? So with the input shape for the fully connected layers or the CNN must be equal, right? So that's why we're going to apply another wrapper on top of the ROIs for the from the feature maps, and that mapper is going to reshape the ROIs to the same size shape, right? So now the ROIs have the same size. We're going to pass it to a fully connected layer, and then the output is going to be, again, for the classification, we're going to do, for example, softmax. For the bounding box regressors, we can use any kind of machine learning, but here we're in a fast RCNN, we're going to apply linear. Okay, so it seems that it is a lot better than RCNN. That's why we call it fast RCNN, because this whole passing the input image to the convnet is only once now instead of being 2,000 times, right? So what are the problems then? The problem is that it still uses selective search. So we didn't fix this part. We didn't do anything about this, the heuristic selective search, which was fixed. Now, so it is still using that selective search to generate the ROIs, right? And it is still detached from the network, right? So again, this thing is not learnable, is not learning during the training process, and it seems that it is doing the job at a completely detached from the network. So the next alternative probably is the RCNN model that can incorporate that thing as well, and this is exactly what the faster RCNN is doing. All right, so what is faster RCNN? In faster RCNN, instead of using that selective search algorithm on the feature map, which, by the way, remember that was a fixed algorithm, right? So in order to use that to identify the region proposals or ROIs, we're going to use a separate network. So that's the innovation here. We're going to use a separate network to predict the region proposal, right? So now this region proposal network, or RPN, it is completely learned, and it's part of the architecture of the model itself. So it is not detached from the CNN, from our CNN, right? So maybe this visualization is going to help us. Again, just like fast RCNN, we're going to pass the entire input image only once to our conv layer, and then we are going to extract the feature maps, and then we are going to pass this feature map to an RPN, region proposal network. And then the output of this RPN is basically some bounding boxes and locations, right? And basically locations and classes. Then because we want to pass it to a fully connected layer, we're going to use our ROI pooling layer to make sure that to reshape those bounding boxes for us. And then finally, at the end of the day, we're going to pass it to our fully connected layer and make prediction, right? So this is what's going on here. The predicted region proposal are then reshaped using ROI pooling layer, and then it's used to classify the image within the proposed region, and of course the bounding box values, right? So here's another representation that might be, again, solidify your understanding. This is our input image. We're going to pass it to a conv layer to extract features. And then this is the feature map out of that layer. We're going to use a separate RPN. It's another network, but it is trainable within the entire model architecture. So this is the innovation part, right? And the output of this RPN of this network is going to be basically the object classes and the bounding boxes. Now we have bounding boxes with the labels. We're going to pass it to the ROI pooling because we want to make sure that they have the same shape to be passed to a bunch of fully connected layers. And of course, the output of these fully connected layers is multi-class classification and the location of those bounding boxes. So this is what the faster RCNN is going to do in order to improve the RCNN and fast RCNN. Okay, here's a slide that compare RCNN-based models, just to recap, right? To make sure that we can see them side by side and we can compare what are the differences between these three models, right? Three architectures. So on the left, we have RCNN. This is a 2014 architecture, by Gershik. And just a year after that, he himself developed the fast RCNN. And a year after that, 2016, Ren et al. They developed the faster RCNN. Okay. So again, at a very high level, what are the differences? So this one, the RCNN was slow because we had to come up with these. We had to pass all these 2,000 region of interest, which were coming from a heuristic algorithm, search algorithm. And we pass all those 2,000 ROIs to networks, right? So we're repeating this process 2,000 times if the ROI number is 2,000, right? It can be even higher than that, right? So as you can see, it was very inefficient, but basically it was so slow, right? The update was that let's do this process only once. Let's look at the input image, pass it to the conv layer once. But the problem of that was that the output of this step didn't have the same shape, right? So we used the ROI pooling to make sure that they have the same shape. Now we can pass it to a fully connected layer and make predictions. And then faster RCNN, this was the fast one. The faster RCNN, the difference between this and these two is that it updated the search algorithm and incorporated that algo in the network, right? So instead of using a fixed heuristic algo, it used a network, which was called RPN, right? Region Proposal Network. And that network is a part of the architecture now. It means that the parameter of that network are learnable, and they're not fixed anymore. So it is more efficient, it's fastest among the RCNN, and yeah, of course it performs better. So the second, the other model that we're going to look into is called YOLO, you only look once, and that model is even faster than the faster RCNN, and it is designed for image processing in real time. Okay, let's talk about YOLO, you only look once algorithm. So YOLO is a real-time object detection, and this is what makes it very useful in practice. It was developed by a team of researchers in 2015 at University of Washington. It is extremely fast because it passes the entire image at once into a CNN. So we are going to deal with only one network. So unlike even faster RCNN that we had to have another RPN, regional proposal network on top of the CNN. So here we only have one CNN. And the key idea behind YOLO is that it uses that single neural network to predict both the bounding boxes and the class probabilities for the object in an image. So for example, the idea is that here's an input image. We pass it to the YOLO, and the output is, but again, the key is that it's going to use a single neural network to do the training and figure out the objects and local locations of the bounding boxes, right? So, and here is a video version of that. And as you can see, this is a real-time object detection, which is very, very helpful in practice. Now let's see how does this interesting algorithm work. So how does YOLO work? So this is our input image, okay? The YOLO divides this input image into grids of cells and predict the presence of object in each of those cells, right? So for example, here we have, I don't know, 4 by 4. Let's say we have 16 of these grids, right? So what is the input shape? It's going to be, let's say each of these grids is 2150 by 1613. Multiply 3, these are the color channels, RGB channels maybe, and we have 16 of them, right? So this is where the input shape is coming from. Then, what is the sample output? So imagine we're looking at, let me use maybe what color? Let's use this blue. So imagine we're looking at this grid number 7. So this is grid number 7. And the output for this grid number 7 are 8 numbers. First of all, is the object detected or not? So in this case, the answer is yes. And then what is that object? So we have 3, imagine we have, this is a 3-class classification, either if that object is a car, it's a light, or it's a pedestrian, right? So obviously here the probability of car is 1 and the rest of them are 0. If the probability of the object is 0, we don't care about the bounding box. Well, obviously it makes sense, right? We don't care about those values. But if the probability is 1, we're going to report these 4 numbers on top of that. So we're already familiar with them, right? Bx, By, Bw, and Bh. What I want you to pay attention is that Bx and the By is clear, right? So for example, we are here. It's 0.8 and 0.9 toward the x and y axis, right? But look at the Bw and Bh. It is greater than 1. What does it mean? It means that it goes beyond this grid 7. Okay, so that's where the numbers 1.5 and 1.2 is coming from. So the width is 1.5, no, 150% of the width of the grid 7, and the height is 1.2 or 120% of the height of the grid 7. Okay, so hopefully these numbers make sense. So this was a sample output. Then the total output of the network is what? What is the dimension of the total output, right? So remember, we are going to have, well, actually, this is where the total size is coming from. I'm gonna break it down to you. But at the end of the day, for this example, we're going to have 8 of these numbers for 16 grids. So 8 by 16. So if I want to break down that 8, where is that 8 is coming from? It's coming from 5 plus C. So 5 is simply the probability of object, if there's an object there or not, and then plus those 4 numbers, Bx, By, Bw, Bh. So here, this is your 5 numbers. And C is the number of classes. These are the probability of classes. So here we are dealing with the 3-class classification problem, either car, light, or pedestrian. So this is 3. So that's where the 5 plus 3 is coming from, 8. And S basically is the size of your, we have 4 by 4, right? So we said that 4 grid here, 4 grid here. So 4 by 4, it's 16. So this is where 8 multiply 16 is coming from. So the output now has 8 multiply 16 values, right? Or things that we need to predict. In other words, the output size is 128. Okay, so I think we already talked about all these bullet points. So if an object is detected in a cell, the algorithm also predicts its bounding box and the class for that object, and the bounding box coordinates and class probabilities are then used to localize and classify the object. So this is in a nutshell and at a very high level what is YOLO and how it does the job. YOLO has become very popular for its ability to perform object detection in real time, and of course it's relatively good accuracy. As you can see, the accuracy might not be the best out there, but because it's super fast, right? You have to sacrifice something compared to other algorithms. It has been used in a variety of applications, including self-driving cars, in a video that you saw in the previous slide, for surveillance systems, for security systems, and image and video analysis. Okay, now we know what is YOLO, how it works. Let's see if it comes with some caveats. And the answer is yes. And the good news is that we can fix them. So one of the caveats of YOLO is that it can't detect multiple objects in the same grid. Just look at this example. Imagine we have an input image with 3 by 3 grid size, and then let's say in grid number 8 here, you want to classify if this is a person, is a car, or a tree, right? So imagine you have 3 classes, you want to classify person, car, tree, right? And then, as you can see for this grid, we don't know what is the output. The output, well, if I use the basic YOLO, the output is going to be one class, either a person or car. Most probably a person here, because in this grid, what do we have? We have legs, we have body, so most probably this grid is going to be classified as person, right? But how can we fix it? The idea is to use anchor box. So anchor boxes, these are just predefined bounding boxes used in object detection algorithm, right? So basically, and we can have, for example, here, these are the different bounding boxes that we are going to predefine them. So here we have 9 of them, 3 green, 3 blue, and 3 yellow. They can have different scales and aspect ratios. For example, the red one, it can have a scale of 0.25. The orange one can, oh, the yellow one maybe, it can have a scale of 0.75. As you can see, the scale is is relative to the number 1, right, 100%. And then the green one can have a scale of, let's say, I'm just making numbers, it can be 1. So let's say this is our 1, and then the yellow one is 0.75 and the red one is 0.25. And they also come with different aspect ratio, right? So for example, they can come with a ratio of 0.5, and let's say this is vertical, or a 1 and 2 horizontal, right? So for example, let me look at the one that we can follow. For example, let's look at the red one. So this one, this might be the ratio of greater than 1, right? Vertical. This is greater than 1, maybe horizontal, and etc., right? So we can play around with these things, but the idea is that it is predefined, right? These bounding boxes are predefined, okay? And now let's see how it works. So the way that it works is that we're going to use these predefined bounding boxes prior to training the object detection model, and the model is then trained to predict bounding boxes coordinates and class probabilities for objects relative to these anchor boxes, right? So for example, here in this input image, we have, let's say we have 9 anchor boxes. So the size of the output is going to be what? It's going to be 5 plus this C number of classes. Let's say we want to go with person, car, and tree. So we have 3 classes, multiply 9 anchor boxes, multiply, what is our grid size? It is 3 by 3. Okay, so this is the output, right? It's 9 by 9 by 8, right? So this is the output size, Okay, and if you want to look at the details of the output vector, how it's going to look like. So let's say for anchor box number 1, it is something like this. No probability of object is there or not, x and y coordinates, and h and w coordinates as well. Not coordinates, the ratio, right? And then is it class 1? Is it probability of class 1, class 2, and class 3? So this is where the 8 number is coming from. Okay. So one advantage of using anchor boxes is that they will allow the object detection model to make predictions for objects of different sizes and shapes, right? Simply because we're looking into different sizes and shapes here using the anchor boxes. Okay. For example, if the anchor box is defined as a square with I don't know, with a side length of 32 pixels, then the model can detect those objects that are smaller or larger than anchor box by simply predicting bounding boxes that are smaller or larger than that anchor box, right? So that's the way to get around if the caveat that the YOLO cannot detect multiple objects in the same grid. So using anchor boxes, check, we can do that. Okay, another caveat of YOLO is the possibility of detecting one object multiple times. And this is happening simply because we are using multiple bounding boxes, right? So what is the solution? The solution is non-max suppression, or NMS, which removes duplicate or overlapping bounding boxes. So let me show you an example. So imagine this is an input image, and we have, I don't know, maybe a bounding box like this is going to come up with a score if it is a dog or not. Obviously it can, right? So maybe the score is lower. So maybe let me write another color. Score is 0.2. Okay, then we can have another bounding box. Let's use another color, maybe, I don't know, simply using this thing, and then the score is 0.3, something like that. Okay, then so in NMS, or non-max suppression, the algorithm iterates through all the bounding boxes in the image and select the box with the highest confidence score, right? So for example, again, this is a score that I was talking to, confidence score, no, basically the probability. Imagine we have 1, 2, 3, 4, 5 of these ones, and then 3 of them has a score greater than 0.4, right? I'm going to keep them. So let's say we keep them. So let's remove the rest of them. Okay. So in the next step, what we do is we're going to remove all other boxes that overlap with the selected box, right? So if we have 3 boxes here, they overlap with each other by certain threshold. So we're going to remove some of them by certain threshold. So for example, I'm going to say that the threshold, for example, is 0.4. If the threshold is 0.4, and then we're going to have 3 overlapping one, right, for the threshold of 0.4. So, and then we're going to pick the best one. So the blue one is going to be the winner, so we're going to use that one. So this is how NMS works, right? And of course, we're going to repeat this process until there's going to be only one box for each object, right? So that's how we are going to figure out, or how we basically fix this caveat of the possibility of detecting one object multiple times using NMS. All right, we are done with the object detection. Let's talk about image segmentation. All right, let's talk about image segmentation. In general, there are 2 types of image segmentation. The first one is semantic segmentation, and the second one is instance segmentation. So semantic segmentation is the process of assigning a class labels to each pixel. So this is what we talked about already, right? So imagine this is your input image, and you want to come up with 4 classes. If it is a sheep, dog, cat, horse. If these animals are detected in the image, right? And we're going to say that, okay, for each pixel, let's look at the, basically based on the pixel's visual characteristics and its relationship to the surrounding, let's label it, right? And then we are going to say that, okay, so it seems that if I do semantic segmentation, these are ships and this is a dog, right? That's it. However, instance segmentation, it's even beyond semantic segmentation. It involves not only classifying each pixel in the image, but also distinguishing between different instances of the same class. So this is where the name is coming from, right? Instance segmentation. So this simply means that here we have, of course, we detected 4 objects, and we know that 3 of them are sheeps and 1 is dog. And we know we have 3. So this is the way that we're going to segmenting 3 different sheeps from each other, right? So this is called instance segmentation. Okay, now to deal with semantic segmentation, we have to come up with kind of new architecture, because remember, this is a new problem now. We want to predict a class for every single pixel in the image, and this is a super high dimensional problem. And on top of that, we want to make sure that the output spatial dimension, let me use the marker. So the spatial dimension might be 256 by 256. The spatial dimension, just height and width, is the same as input, right? 256 by 256. So for that to happen, we're going to use a new architecture, which is called FCN, Fully Convolutional Network. So in an FCN, it has 2 steps, encoder part and decoder part. In FCN, the input image is passed through a series of convolutional layers, right? So we're going to pass it to a bunch of convolutional layers, and we know that as we go deeper in the network, the spatial size is going to get reduced, right? So this is the encoding part. But basically, this encoder is going to extract features from the image and, of course, reduce its spatial resolution. So I don't know, maybe from 256, we get into something like, if it is very deep, we get 5 by 5. Okay, if the network is very deep, right? Then our job is to reshape it back to the original size. So for that reason, we're going to use convolutional transpose layers, that we talked about in the first part of the theory, in the second part of the theory lectures, right? So that's the decoding part, which basically use bunch of transposed convolutional layers. So these are transposed convolutional layer, simply to upsample the feature map. So these are the feature maps. So we are going to upsample them. to the original resolution of the input image. So this is the decoder part, right? And of course, it's going to output a dense prediction for each pixel in the image. So we know that, well, the dimension, I don't know, the spatial dimension is 256, 256, and for each pixel, we have a label now. Okay, so this is how this new network, which is called fully convolutional network, helps us for the semantic segmentation. And just one last thing I want to say here is that, look at that, look at this architecture. In this architecture, there is no fully connected layers. And do not confuse these acronyms, right? So fully connected layer. And just make sure that you don't confuse it. There's no fully connected layers, and we only have, convolutional layers. So that's why we call it fully convolutional network. And here is just a quick reminder for those of you who didn't get a chance to watch the theory lecture part 2 of this module. So here's how transposed convolutions are working, right? So they're also known as deconvolution simply because they are upsampling or upscaling. This is the inverse version of the convolutional operation. We know the convolutional operation usually downsample image. Now we want to upscale it, upsample it. So imagine we have a 2x2 input. We want to transform it to a 3x3. We're going to apply a 2x2 filter and apply it to different parts of the input individually, and then we're going to add them up together to come up with our new output, which is upscaled. And I guess there is no need to say that the semantic segmentation has huge applications out there. So for example, in healthcare, at the top, you're looking at segmenting the brain, the tumors in the brain. So this is how the model is going to segment out the damaged part of the brain. Or we can look at this one, which is segmenting out cancer regions or maybe affected part of the blood, right? So yeah, this is in healthcare. We can also look at the semantic segmentation application in self-driving cars. And this is, for example, how it's going to look like, right? And again, we can do it in real. So this is a real-time example. Imagine we have this many classes, right? Road, sidewalk, building, wall, fence, and these are color-coded, right? And then as the car is just passing through the streets, all these things should be segmented in a real time. All right, so this was the application of semantic segmentation, and at the very high level, what is the architecture that we should use for semantic segmentation? Okay, the next one and the last topic that I want to cover in this lecture is image captioning. All right, as we stated earlier, image captioning is just a task of generating textual description of an image, of course, based on the objects and actions which is depicted in the image, right? So it usually consists of two steps, right? Basically, there is a computer vision component of that and a natural language processing component of that, right? So there is a visual model. The visual model, typically we can do CNN, and this visual model is going to extract features from the input image. So this is your input image. Let's say 224, 224, 3. We're going to pass it to a CNN, and then we're going to extract features, flatten those features, and then pass. So this is the computer vision part, or the visual model. Then we're going to pass that thing to the language model, or natural language processing part. And that's going to process the features and generate the captions, right? Usually and typically we can use RNN and LSTM. Don't worry about this part. We haven't covered it yet. So that's actually our module 6 when we go over the recurrent neural networks. All right, let's conclude this exciting module of the course with the applications of image captioning. I bet you can think of many, many more examples around yourself when it comes to image captioning, but here's just a few. We can go ahead and generate captions for social media posts and websites. So this is pretty good, right? For example, I don't know, there's a blind person and then they can wear glasses, and then with that glasses, they can hear whatever is happening in their surroundings. So this is priceless, right? We can go ahead and create metadata for image search engines, right? And we can also improve the accessibility of images for people with visual impairments. So again, the application is huge, right? So for example, the blind people can simply wear a gadget, and then that gadget can help them to find their way better. They can run more safely, they can walk better, and yeah, things like that. This is what makes this field very exciting and interesting to me, because it can help so many people out there. Okay, that was it. This was our Module 5, Deep Computer Vision. So I tried to go through the theories at the very high level from basic to advanced, and we also covered some of the applications with Python. However, just keep in mind that for the advanced part of the lecture, when we talked about, let's say, image captioning, semantic segmentation, I will not provide the Python code simply because it's beyond the scope of the course. But yeah, I bet you can easily find many useful resources out there. And however, for the rest of, for the more basic and even for the transfer learning, we covered all these things in the Python. Okay, until the next one, take care and have a good one.